Hi everyone, welcome to today's lesson on exponential functions and their graphs. So we're going to start by talking about what an exponential function looks like. So an exponential function is in the form f of x equals b to the x, where the base is what we call the constant b, and it has to be a constant that is greater than 0, so it has to be positive, and it cannot equal 1. And then the exponent that you have is any real number. So we want to determine which functions are exponential functions, and for those that are not, explain why they are not exponential functions. So you can follow along in the guided notes that you have. So 2 to the x plus 7. If we're looking at the base, it's a constant, it's positive, and it's not equal to 1. So it is a exponential function. X squared, the base is x, which is a variable and not a constant. So this is not an exponential function because the base is not a constant. What you're actually looking at, if you recall, is a quadratic function. Part C, h of x equals 1 to the x. 1 is a constant, but the base to be an exponential function cannot equal 1. So this is not an exponential function because the base is equal to 1. And then part D is not a function for similar reasoning, not an exponential function for similar reasoning as part B because the base is not a constant, it's a variable. All right, let's take a look on the next slide at E, F, G, and H. So part E, h of x, if we look at the base, what is being raised to that power of negative x is base 10. 10 is a constant, it's positive, and it's not equal to 1, so yes, that is an exponential function. In part F, if we compare part F with part G, you want to be careful. There is a difference because of the fact that one has a parentheses around the negative 3 and the other does not. So in part F, what's really happening is the positive 3 is being raised to the x plus 1 power and being multiplied by a negative. So the base is 3, which is positive. It's a constant, and it's not 1, so it is an exponential function. So I would kind of highlight that and be careful. That's the point of the parentheses in mathematics. It's a common misconception. The negative is a multiplier, if you think PEMDAS, after the 3 is being raised to that power. Whereas conversely, if you look at in part G, the negative 3 is all being raised to the x plus 1 power, and we know that because the negative 3 is all in parentheses. So therefore, it's not an exponential function because the base is not positive. And then part H, 2x minus 1, if you recall, that's actually a linear function. Your y equals mx plus b, so it is not an exponential function. All right, so let's take a look at some graphs. So you want to graph these two exponential functions, which you did when you were comparing on your math lab in today's class. So 2 to the x. You want to pick 3 points to do this. You can use more than 3 points to evaluate any function, but the kind of 3 main key points that you're going to use is to the negative 1, 0, and 1. So 2 to the negative 1, remember, negative exponents reciprocate the base, so that becomes 1/2. 2 to the 0 is anything to the 0 power is always going to be 1. And then 2 to the first just gets you 2. If we look at negative, 1/2 to the x, 1/2 to the negative 1 power, again, that reciprocates the base. So that makes it 1 over 1/2 to the positive first, or in other words, 2. 1/2 to the 0 power, again, anything to the 0 power is always 1. And 1/2 to the first is itself, so it's a half. So if we kind of compare these graphs here, 2 to the x, which you can see in purple, is increasing from left to right. So an increasing graph from left to right we call exponential growth. And in green here you have the graph of 1/2 to the x power, and that graph is decreasing from left to right. So if we think of our increasing and decreasing intervals from previous units, we call that exponential decay for decreasing. All right, so on the next slide we're going to kind of talk about characteristics of exponential functions, and then we'll get to some transformations. So if the base of your exponential function is greater than 1, so like 2 to the x that we just saw, then the function will always increase from left to right, and this is what we call exponential growth. So that was the purple graph on the previous slide, increasing from left to right. If the base is between 0 and 1, like we saw with 1/2 to the x, then it's decreasing, it's falling from left to right. So this is what we call exponential decay. So those are the two types of exponential functions that you can have. You might have noticed in both those graphs and also from your math lab activity that the parent function without any transformations will always pass through the point 0, 1. In other words, it will always have a y-intercept of 1. And also you might have noticed that the graph will always approach the x-axis, but it will never actually cross it. So there is that horizontal asymptote at y equals 0. Of course, this is referring to the parent function. So of course, if there was a vertical translation which moves your graph up or down, your horizontal asymptote will also have to move up or down with it. The domain for your exponential functions is -infinity to infinity. It's never stopping left or right, which you again probably observed in your math lab activity. And the range is going to be where the asymptote is to infinity. So for our parent functions, it's going to be 0 to infinity. And since we're never reaching that asymptote, 0 is not going to be included. So 0 is in a parenthesis if we recall interval notation. All right, so let's take a look at kind of generalizing some key points here. Of course, you can use more than 3 points, but I really only need you to use 3 points when graphing. Anything to the -1 power is going to reciprocate the base, so 1 over the base. Anything to the 0 power is 1, and anything to the first power will just get you the base itself. So those are the points we're going to be using when we transform our graphs. And if we recall transformations from our earlier transformation unit, and you have this to refer to in your notes, so I'm not going to spend a ton of time talking about this, but just recall that x plus c, something being added or subtracted directly to x, so in this case our exponents, is moving your graph left or right. And remember, it goes in opposite direction. So this x plus c is the same as saying x minus a -c, which really is what's causing it to move left. The other thing that you want to recall is that a multiplier in the front is going to cause a vertical stretch. And if it's bigger than 1, it's going to stretch it. If it's between 0 and 1, it's going to shrink it. Whereas horizontal is backwards. So any multiplier directly happening to x is going to cause a shrink if it's bigger than 1, but a stretch if it's between 0 and 1. Because we are actually dividing our x coordinates by c instead of multiplying. And the only other thing you'll want to recall from your previous units is the order in which you transform. So you want to do horizontal, stretch, shrink, reflect, and vertical translations last. All right, so let's take a look at some graphs here. So the first example we want to go through is graphing -2 raised to the x plus 3 minus 1. So we want to start by finding the 3 key points for the parent function. Your parent function is the function without all the extra stuff being added or subtracted to it. So in this case, that's just 2 to the x. And we already graphed that, but let's review. We're going to plug in -1, 0, and 1 into our parent function. So 2 to the -1 reciprocates the base, so we get a half. 2 to the 0 is 1, and 2 to the first is 2. Then we want to identify the transformation. So what's happening to our graph? Well, our graph is moving left 3 units, and it's being reflected across the x-axis, and then it's going down 1 unit. So once we have those 3 key points and the proper order of the transformations, we can start at these 3 points and move accordingly. So let's take a look on the next slide. So starting at 0, 1 here, if I go ahead and move that 3 units to the left, and I reflect across the x-axis and move down 1 unit, I'm now sitting at -3, -2. And if I take another ordered pair from my parent function, 1, 2, and I move 3 units to the left, and I reflect across the x-axis and I move down 1 unit, I'm now sitting at -2, -3. And then that last point, if I take -1.5 and I move 3 units to the left and I reflect across the x-axis and I move down 1 unit, then I have the ordered pair -4, -1.5. So there's our graph. Now if you recall, your parent function normally has a horizontal asymptote at 0, but you moved your graph down 1 unit. So any vertical translation will cause your graph to move up or down. So we have y equals -1, which is where you can see our graph that we just graphed in blue here is approaching but not hitting. The domain, it's never stopping left to right. So we have all real numbers, or -infinity to +infinity in interval notation. And the range, because it was reflected, the lowest it's going is -infinity. And as I move up, I'm going to get closer to that horizontal asymptote of -1 without actually reaching it. So it's going to be -infinity to -1. All right, let's take a look at what we call the natural exponential function. We're going to do more with this later, but all you really need to know right now is that e to the x is called the natural exponential function. It's an irrational number. We can approximate it to 2.72 about. It's just like when you approximate your irrational number of pi to 3.14. So when you see e to the x, e actually represents a number just like pi does. And you have the button E on your calculator, which is located right above the ln button. So if you hit second ln on your graphing calculator, it will give you the decimal of E. All right, so last graph here. If we want to graph e to the x minus 3, then we're going to start by the parent function of looking at e to the x. So e to the x is, let's first take our key points. So e to the -1. If I plug in -1 in for x, so 1 over e to the first, or 1 divided by about 2.72, you're going to get about 0.3679 depending on how you're rounding. Anything to the 0 power will produce 1, and e to the first will get you that number 2.72. If we then go ahead and look at our transformations, the -3 is going to move it right 3 units. So if we start, and again, let's look at the really non-decimal ordered pair here, 0, 1. If I move that right 3, then I am now sitting at 3, 1. You can see the same for the decimal. This 1, 2.72 ordered pair moved right 3 is now sitting at 4, 2.72. Okay, so just approximate those decimals. They don't have to be perfect. And in purple here, you can see your e to the x minus 3 graph. The horizontal asymptote is still sitting at 0 because there was no vertical translation. And then the other graph that they want you to graph on the same coordinate plane in your notes, which we'll do on the next slide, is h of x, which is -e to the x. So first we're going to focus on the parent function. We already talked about those 3 main points, 3 key points. Plug in -1, 0, and 1. 1 over e is 1 divided by 2.72, so there's our approximation. That negative out front is going to cause it to reflect across the x-axis. And so if we take our ordered pair 0, 1 and we flip it across the x-axis, we are now sitting at 0, -1. And then you can also reflect those decimal points. So there it is in purple. Notice our horizontal asymptote is still at y equals 0, but because we reflected it across the x-axis, our range is now -infinity to 0. Because it's the lowest it's going is to the negatives, the negative y values. So that's it for your guided notes. I want you to now take some time and complete the Google form questions. The questions that you will have attached on your worksheet, you can do your work there, and I'll check your work in the next class, and then you'll submit the multiple choice answers in Google form so that you can get immediate feedback and we can go over any questions you may have. I'll see you all tomorrow. Good luck.